Hi guys, it's Miss Cassano, and today we're going to review for the Unit 5 test. I'm going to do some questions from the review sheet, so feel free to skip around. Yeah, let's get started. So the first one is to simplify the following square root. It's the square root of 50, x to the 5th, y to the 8th. And the way that we think about these is first we go to simplify the number under the radical. So we find the biggest perfect square that will fit into 50. The biggest perfect square that fits into 50 is 25. So rad 25 times rad 2 would give us rad 50. And the way that we know that that's the biggest perfect square is when we start dividing perfect squares into 50, when we divide 50 by 25, we get 2, and 2 can't be simplified by perfect squares anymore. It's too small. So that's how we know we got the biggest perfect square. So the square root of 25 is just 5. Rad 2 stays the same, so that turns into 5 rad 2. So our radical now looks like 5 rad 2, x to the 5th, y to the 8th. Now, to take the square root of variables raised to an exponent, we want to break them up into multiples of 2. So that would look like 2x to the 4th times x to the 1st, and y to the 8th is already a multiple of 2. The reason we do that is because two perfect exponents that are perfect squares are even. So then we just divide them by the index. 4 divided by 2 is x squared, so the square root of x to the 4th is just x squared, so x squared comes out. And y to the 8th divided by 2 is y to the 4th. And what's left under the radical is 2x. The next one to simplify is a cubed root, and our procedures stay the same as when we simplify a square root. However, instead of trying to find the biggest perfect square to fit in the number, since we're taking a cubed root, we're finding the biggest perfect cube. So the biggest perfect cube that can fit into 16 is 8. 8 times 2 gives me 16. The cubed root of 8 is 2. Cubed root of 2 is just 2. So simplified so far, we have 2 times 2. This extra 2 comes from the outside. I think that's the biggest mistake that you might see, is that you forget that number on the outside at the beginning of the question. So 2 times 2 rad 2, which is what we got when we simplified. And then just rewrite the variables. A cubed, b to the 4th, c to the 5th. Now, when we were taking the square root of variables, we split them up into multiples of 2. Because all even numbers, all even exponents are perfect squares. When we're taking cubed roots, all perfect cubes are multiples of 3. So we're going to set up our exponents to be in multiples of 3. So 2 times 2 is just 4. So 4 cubed root of 2. A cubed is already a multiple of 3. B to the 4th, I can split it up to be b to the 3rd times b to the 1st. And c to the 5th, I can split it up to be c cubed times c squared. A cubed, you just divide the exponent by the index. Since it's a multiple of 3, 3 divided by 3 gives me 4a. B cubed, 3 divided by 3, b, and c comes out. And what stays under the radical is b, 2bc squared. So the next simplification problem we have is to simplify a product. So when we're doing products of radicals, you multiply what's on the outside and you multiply what's on the inside. So clearly here we just have stuff on the inside. So all you're going to do is multiply across. So 5 times 6 times 2 gives you 60. X times x, x to the 4th times x gives you x to the 5th. Y times y to the 6th gives you y to the 7th. Z times z cubed gives you z to the 4th. Now clearly that's not in simplest form, so we're just going to follow the same steps. We're going to find the biggest perfect square that fits into 60. The biggest perfect square that can fit into 60 is 4, and 4 times 15 gives you 60. We know 4 is the biggest perfect square that can fit into 60 because when we divide 60 by 4, we get 15, and that can't be broken up any further by perfect squares. So the square root of 4 is 2. The square root of 15 is just 15, so that stays the same. I'm going to rewrite this now with my new simplified number. So 2 rad 15, x to the 5th, y to the 7th, z to the 4th. And now we need to start simplifying these exponents. Since we're taking the square root, we're going to break up these exponents into multiples of 2. Even exponents are perfect squares, so that's why we're doing that. 2 rad 15, x to the 5th, I can split it up into x to the 4th times x to the 1st. Y to the 7th, I can split up into y to the 6th, y to the 1st, and z to the 4th is already even, so I'm just going to leave it. The square root of x to the 4th, well, you divide 4 by the index of the square root, which is 2. So 4 divided by 2 is x squared, so 2x squared. I'm going to skip x to the 1st because that's not a perfect square. Y to the 6th, the square root of y to the 6th is y cubed. You just divide it by the index, which is 2, because we're taking the square root. Y to the 1st isn't a perfect square, so I'm just going to skip that for now. And the square root of z to the 4th is z squared. And then my non-perfect squares live inside my radical, 15, x, and y. And that would be your final answer in simplest form. Simplifies and rationalize the following. So 4 over 5 minus rad 7, the way we rationalize this is we multiply by the conjugate. And the conjugate is when you take a binomial and you just switch the sign in the middle. So I'm going to multiply 4 over 5 minus rad 7 times its conjugate. And the reason why we're using the conjugate is because whenever we multiply by a conjugate, we usually get a pure real number. And when we rationalize, we're trying to get rid of the radical. So in order to get rid of the radical in this case, we have to use the conjugate to get a pure real number. So the top turns into 4 times 4 plus rad 7. And the bottom is 5 minus rad 7 times 5 plus rad 7. I'm just going to quickly distribute the top. Oops. 4 times 5 is 20. 4 times rad 7 is just 4 rad 7. The bottom, you could either double distribute, FOIL, or use the box. I'm going to use the box method because I think it's just neater and more organized. 5 negative rad 7, 5 positive rad 7. And then you're just going to work your way through the box. So I just multiplied my way through the box, and I got my product as 25 negative 5 rad 7 plus 5 rad 7 minus rad 49. Right in the middle here, minus 5 rad 7 and positive 5 rad 7 are just going to cancel, and that's going to leave us with 25 minus 49, rad 49. 25 minus rad 49 is going to turn into 7. So this just is 18. So our fraction becomes 20 plus 4 rad 7 over 18. Now we're done with the radical part of it. However, these all share multiples of 2. So we could simplify. It would turn into 10 plus 2 rad 7 over 9. And that would be your final answer. So now we're going to rationalize 2x over the cubed root of x. Since we're rationalizing a cubed root instead of a square root, we can't just multiply by the denominator and move on. It's a little different, and here's why. When we are taking, let's say we'll rationalize something that's like 1 over rad x. we multiply the top and the bottom by rad x times rad x. That turns us into rad x over the square root of x squared. Now we know that the square root of x squared is just x. So that gets rid of our radical in the denominator. We have a quote-unquote real number because x is just a real number. In the denominator, we're good. However, if we were to do that with x, the cubed root of x, it wouldn't work out that nicely. We need to get it to look like the cubed root of x cubed, because the cubed root of x cubed gives us an x. So when we're rationalizing something with a higher index, we basically have to make as many copies as that index. So right now we have one copy of x. Well, since I'm a cubed root, I have to make 2 more copies of x to get it to be x cubed, and then for it to be able to pop out of this denominator. So 2x over the cubed root of x. In order to rationalize this, I have to multiply by the cubed root of x squared over the cubed root of x squared. 2x times the cubed root of x squared over the cubed root of x cubed. The reason why we're multiplying by x squared and not just by the denominator of the cubed root of x is because we need to get it to be x cubed under this cubed root for it to pop out just an x. And then at the top we have 2x over the cubed root of x squared. 2x and x, that cancels, so you're just left with 2 cubed root of x squared. And that's it. Simplify the following using fractional exponents after place in simplest radical form. So this is 16x all raised to the 1/2. And I just want to point out that this is not the same as this. And this was a question on your review sheet, and there's a reason why I gave you both of them. This one is just the x being raised to the 1/2. So the 16 has nothing to do with this radical, this fractional exponent. So if I were just to rewrite it as a radical, the 16 would have nothing to do with the radical, and the x would just be under it. This one, however, I'm just going to erase this, is attached to the 1/2. So this fractional exponent, which if I remind you, it's power over root. So this tells us that the root has an index of 2, and it's all being raised to a power of 1. So 2 square root, this 16 would be in it, and so would this x. And that's because it's all being raised to the 1/2 power. Unlike this one, when the 1/2 was just attached to the x. So now, obviously, this is not in simplest form. We can simplify this further. 16, the biggest, 16 is a perfect square. So 4 would just pop out, and our x would just stay inside. And that would be it. Simplify y to the 9th to the -4/3. So here we have a variable being raised to an exponent, and that's all being raised to a fractional exponent. Now, when we have exponent to exponent, and this is one of those exponent laws we went over and we had homework on in class, we multiply the exponents. So my biggest tip to you when dealing with fractional exponents would be to leave it in fraction form while you're working, and then put it in radical form at the end and then simplify. So 9 times -4/3, because it's exponent to exponent and we're multiplying, would give you -36/3. There's a couple different things you could do here. First, I'm going to deal with that negative. A negative exponent tells us to switch the location. So since I have a negative exponent and my variable that it's attached to is in the numerator, that means I'm going to drop it to the denominator. If I had a negative exponent attached to the variable in a denominator, it would get risen to the numerator. So it just flops the position. So y to the -36/3 turns into 1 over y to the 36/3. Now, obviously, we can't leave it like that. It says leave in radical form. So I'm just going to transform this back. So using my power over root, my root index is a cube, and my y is being risen to a 36. You could stop here and rationalize. However, that might be a little difficult because it is a cubed root and you have y to the 36 under there. Or you can notice that 36 is a multiple of 3. And you could just, 36 would be a perfect cube. Y to the 36 would be a perfect cube because it's a multiple of 3. So you can just divide the exponent by the index and you would get y to the 12 as your final answer. So we are going to solve the following radical equations, state the solution as a set. If there's no solution, we're going to do something called the empty set, and you must always check your answers because we get something called extraneous solutions, meaning they make it invalid. So in order to solve radical equations, basically we're going to look to undo the square root, and all that means is we're going to square a square root or we're going to cube a cubed root. So in order to do that, we need to isolate the square root. So I'm just going to start by doing that. I'm going to move over my 1. So I'm left with radical x plus 11 on one side, and then x minus 1 on the other. Now, since I have my square root on one side and everything else on the other, I can square my square root because we know that a square undoes a square root, and whatever I do to one side of the equation, I have to do the other. So my x minus 1 gets squared as well. When I square my square root, it cancels, and what's underneath comes out. And then x minus 1 squared, you could either FOIL this, double distribute, or do the box method. I prefer the box method because it's more organized and easier to see. So x minus 1 times x minus 1, and you're just going to work yourself through the box. So after I work myself through the box, I get that x minus 1 squared is equivalent to x squared minus 2x plus 1, so I just rewrite that under where it goes. So I have a polynomial on one side that's x squared, a trinomial on one side that's x squared, and then I have these extra terms x plus 11. So I'm thinking that I'm going to probably move these over and try to factor. So I get x squared minus 3x minus 10. I have a trinomial, so I'm going to always use the AC method. So I'm going to take my first term, multiply it by my last term, which is negative 10x squared. And we're going to find the number that adds to the two numbers that add to negative 3 and multiply to negative 10. I'll give you a second to figure out those numbers. So the two numbers that add to negative 3x would be negative 5x plus 2x. And the two numbers that would multiply the negative 10x squared are negative 5x times 2x. So now you're just going to substitute those in for negative 3x. Negative 5x plus 2x. This is equivalent to negative 3x, so it's fine that we're doing this. Minus 10. Split it right down the middle and start factoring. Factor your first group of terms. You can pull out a GCF of x, x minus 5, and factor your second group of terms. You can pull out a GCF of 2, x minus 5. These parentheses right here should always match, and they do, so you know you did it right. So after you're done factoring, you get that your factors are x plus 2 and x minus 5. And this is all still equal to 0. So once you're here, you have your two factors that are equal to 0. You're going to take each one and set them equal to 0 and solve for x. So once we solve for x, we get x equals negative 2 and x equals 5. However, those could potentially not be the answers to our question. We have these things called extraneous root, and for every reason, these extra roots, these extra solutions get introduced while we're solving these equations. So we always need to check our answer. So you do that by just taking your x values and plugging them into the original equation. So rad x plus 11, I'm going to do 5 first. So 5 plus 11 plus 1 equals 5. So you can plug those into your calculator or do it mentally. when you figure that out, you get that 5 does in fact equal 5, so we know this is a solution of our equation. And then we're going to plug in x equals -2. So -2 plus 11 plus 1 equals -2. Once you check it, you get that 4 equals -2. That is not a true statement. 4 does not equal -2. So we know from this that x equals -2 cannot be a solution. So we reject it. It's extraneous. It's not valid. So the only solution we get here, and I'm going to put it in a set because that's what my question asked me, is x, the solution of 5. So this next radical equation we are going to solve is not a square root, but it's a cubed root, but that doesn't change anything. We're still going to first isolate the radical, and then we're going to uncube it instead of unsquare it, but you still just take the cubed root, and then solve for x and check our solutions. So the first thing we're going to do is isolate the radical. So I'm just going to subtract 3 from both sides and get the cubed root of 4x minus 8 equals -2. Since I have my cubed root all by itself, I could take the cube of it to undo it. And I'm also going to take the cube of the other side, because whatever I do to one side, I have to do to the other side. So my cube and my cubed root cancel out, and what's inside comes out, 4x minus 8. The cubed root of -2 is -8. Add 8. Add 8 to both sides. You get 4x equals 0, so x equals 0. You're not done though, you must check. So that means we're just going to take our x value and plug it back into our original. 3 plus the cubed root of 4 times 0 minus 8 equals 1. So 3 plus the cubed root, 4 times 0 is just 0, minus 8 is -8, equals 1. If you put the cubed root of -8 inside your calculator, you would get out -2. And the reason why we don't do our I thing is because I is only true when we're taking square roots or even roots. If we're taking odd roots or cubed roots, you can take that as negative numbers. So you get 3 plus a -2 equals 1. 3 minus 2 is 1. 1 equals 1. It checks out. So 0 is your solution. The domain of the following radical function in set builder notation. So the domain of a function is where the function exists, where it's defined. And a radical function is defined on all real numbers. So we have to find where this radical doesn't exist. And we know that radicals are imaginary, or square roots are imaginary, when they have a negative under the radical. So our job is to find out what is going to make this under the radical negative. So we're going to solve for the values of x, so 8x minus 16, that give us a value less than 0, because that's going to give us a negative under our radical, which is going to give us an imaginary number, which means that our function is not defined, meaning it's not in our domain. So I'm just going to solve for x. I know that if I add 16 to both sides, I can avoid dividing by a negative. However, I want to divide by a negative just to show you how to handle it. So I'm going to subtract 8x to both sides. So leaves me with -16 is less than -8x. And I'm just going to divide by -8. -8 divided, so you get x, however, it's a negative, so you have to flip it, is less than 2. So for the values of x that are less than 2, so if I plugged in 1, if I plugged in 0, if I plugged in -1 into this original guy, I would get a negative number, which would give me an imaginary number and would make my function not defined. So my domain wouldn't include these numbers because it would make it negative and it would make it not defined, and my domain is where it is defined. So my domain would have to be all the numbers that are not in that. So it would be x is greater than or equal to 2. f of x equals negative rad x plus 4 minus 2 on the given axis. So part A is just saying to graph, and the way that I would like you guys to approach that is to set up an x, y table. So x, y, and like that. You can use your calculator to get these values, so all you would do is just plug in this equation into your y equals, and then hit second graph or table. So go ahead and generate that table of values. I would suggest only using the whole numbers. Like, I wouldn't worry about those irrational, ugly numbers. Just use the whole numbers. All right, so I just generated my XY table, and basically all I did was look from negative 10 to 10 on my X values, because that's all you're given on this grid. You're given up to 10 and then down to negative 10. They had error messages all the way up to X equals negative 4, I believe. Or they were irrational numbers. So I started at negative 4, and then I just went all the way up until 10. However, they were irrational numbers, so I stopped at 5 because that was the last whole number. So yeah, now all you're going to do is plot those points and sketch the graph. All right, so this is my graph of the function f of x. So now we're ready to move on to part B. So part B is asking for the domain and the range of the function in set builder notation. So the domain is the set of all x values that this function includes, and the range is the set of all y values. So let's start with the x values. Our function, we got some error messages at x equals anything above negative 4. So our function begins at x equals negative 4, and it goes on and on and on, and encompasses all of these x values, and it keeps going and going and going pretty much forever. So it goes on to infinity. So our domain is the values of x such that x is greater than or equal to negative 4. So it includes all those values bigger than negative 4. Anything smaller than negative 4, like on this side, isn't included because it does not, our function is not defined there. Now let's look at our range. So our function highest point is right here. That would be negative 2. And our function continues to go down because it's flipped all the way till negative infinity. So our range would be all the y values such that y is less than negative 2. Because it goes down and down and down and down forever and ever and ever. These y values up here are when the function is undefined. So everything bigger than negative 2 is when it's undefined. Everything smaller than negative 2 is when it's defined. And the last part is to determine the transformation that takes y and maps it onto f of x. That takes our parent function, which is just the square root of x, and maps it onto f of x. So f of x is what we just graphed right here. So I'm just going to erase all these lines so we have a clear picture to look at. You can do this question one of two ways. You could either just look at the equation that's given and go left to right and say, well, I have a negative here, I have a number in here, and I have a number out here, and remember what those transformations are. Or you can plot your parent graph real quickly, which I will do. All right, so all I did was just plot y equals rad x because that's our parent graph. That's the most simple version of our function. Like I said, you can do this one of two ways. You could either just look at this guy up here and remember those transformations when you move left to right, or you can do it based off the graph. I'm going to use the guy up there. So the first thing we come to is our negative sign in the front of our function. That negative tells us that we flipped it over the x-axis, and clearly our parent graph's square root of x and our transformed graph are mirror images of each other. They're flipped. So flip. We keep going and we come across this guy right here. It's a positive 4. Now the 4 is inside our function. It's within the square root. So that means it's going to be moving left or right. It's going to be moving on our x-axis. So this positive 4, when we're moving left to right, our signs are reversed. Normally we associate the positive direction to be the right and the negative to be the left. However, when we're doing transformations, the left is the positive direction and right is the negative direction. So this positive 4 is telling us we're moving left 4 units. And it's very clear here that our parent graph started, and after we transformed it, we ended 4 units to the left. And the last thing we come to is this -2 on the outside. This -2 tells us that we're moving down 2. And it's very clear that our parent graph starts at -2 or is down 2 units from where our parent graph was. The equation below represents the graph shown. So we're given a graph of some obviously square root function because those are all the equations in the multiple choice questions. And basically they're asking which equation represents the transformations it's gone through. Its parent graph is going to be y equals the square root of x. So one little tip I gave you guys in class is to maybe sketch in the parent graph so you can see how it's transforming. So I'm just going to do that really quick. Okay, so I just wrote in black this function right here, y equals rad x. Rad x is the simplest form of a square root function, and all the transformations happen based off of square root of x. So now we're just going to work through these options and see which one matches the transformations that's occurred. So obviously our square root of x and our transformed function are kind of flipped. So that means they've been flipped over the x-axis. So we can already get rid of choice D, because in order for our parent graph to be flipped, we have to transform it with a negative in front of the function, which is what that tells us. Our parent graph starts at 0, 0, and it's moved to the right to start over here. So when we move to the right, when we're transforming, we know that that's a negative direction. So we can also get rid of choice A because that has us moving to the left. Lastly, our parent graph has moved up. So we can get rid of choice C because that has us moving down. So choice B is the equation that has the parent graph being flipped, being moved to the right 3 units and up 4, which is how we get to this function right here. You can also plug these into your calculator and just match the picture.